Okay, so we have a couple more rules of probability, and then I have to cover random variables and the binomial random variables. So we have what we call the addition rule and the multiplication rule. Okay, so let's start off with the addition rule. Okay, so if we have two events A and B, then we say the probability, so two events, the probability of A or B, and whenever we say or, it's an and or. Okay, so in English we might say, do you like chocolate or vanilla? And what we're saying is, pick one. Okay, but in statistics when we say or, it's this or both. Okay, so or is always it's an and or. Okay. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. So if we have a Venn diagram, if this region represents A and this region represents B, this overlap would be A and B. Okay, the overlap region, A and B. So if I just did the probability of A plus the probability of B, then I would have too much area because I've double counted the overlap. So that is why I subtract off the overlap there. Okay, so we have probability of A or B. And then we have the special case where we have no overlap. And these are known as mutually exclusive or also known as disjoint events. And that essentially means that the probability of A and B is equal to 0. Okay? And so in that case, the probability of A or B is equal to the probability of A plus the probability of B. So if I say, I'm making up numbers here, but if I say 40% of households own a dog and 35% of households own a cat, and I say what percentage of households own a cat and or a dog, or basically a cat or a dog, your answer would be? So 40% of households own a dog, 35% of households own a cat. What percentage of households own either pet? Your answer would be, your answer should be, I can't tell, there's not enough information, okay? Because can someone own both a cat and a dog? Yes, okay? So all I've given you so far is that the probability that a household owns a dog is 0.4, and the probability that a household has a cat is 0.35, and I'm asking for what is the probability of dog or a cat. Okay. And because the households can own both, we need to know how much overlap there is. Okay, so what we need to know is that the probability of someone household having both a cat and a dog, and let's say this is 15%. Okay, then we can answer this question. Okay, then this would be 0.4 plus 0.35 minus 0.15, and then I would get 0.6. Okay. If you just added 0.4 plus 0.35 and said 0.75, that would only work if this were a place where you can have dogs but not cats, or cats but not dogs. Okay. Yes?
For the mutually exclusive and disjoint events, is that, are they interchangeable?
Yeah, they're synonyms. Okay, so some textbooks say disjoint, some textbooks say mutually exclusive. Just get used to seeing one or the other. Okay.
So what if you wanted to include people who had both dogs and cats? Would it be plus?
So people who have both cat and dogs is this.
Right, no, I know, but in the, for dog or cat, you said that the minus 15% are people who have both, right? So you're not, in that 0.6, you're not including people who have both dogs and cats?
I am.
Oh, okay.
I am including. So so this includes so I've got dogs, cats. Okay. So in this, I'm including people who have dogs only, people who have cats only, and people who have both. Okay. What if I ask what percentage of people or what percentage of households have dogs only? Your answer would be so. Percentage of households that have dogs is 0.4, and percentage of households that have both cats and dogs is 0.15. So this entire circle adds up to 0.4. So if I've got 0.15 in this area, I have 0.25 right there. Okay, and if this entire circle for cat is 0.35, I have 0.2 right here. Is that also okay? So another way I could get this answer would be dogs only, which would be 0.25, plus cats only, which would be 0.2, plus has both, so that would be 0.15, and that would also give us 0.6. Okay. But I think to get the 0.25 and the 0.2 required some extra steps in our head. So a straightforward way to get us the answer would be cats or dogs. And this is an and or again. So when I say cats or dogs, it's cats or dogs or both. So that's 0.4 plus 0.35 minus 0.15 is 0.6. Okay. So what percentage of households have neither cat nor dog? No cat and no dog. 40%, 0.4. Because everything adds up to 1. So probability of no cat and no dog . 0.4. So, okay. And then we have the multiplication rule. We already covered this, but we have a special case that I want to go over. So we said the probability of A and B is equal to the probability of A times the probability of B given A. And this is always true. We have a special case. Okay, and that is for independent events. Don't get independent events mixed up with mutually exclusive or disjoint events. They are very different. Independent means that events A and events B have no influence on each other. The outcome of event A has no influence on the outcome of event B, and vice versa. The outcome of event B has no influence on the outcome of event A. So, if I tell you that events A and B are independent, okay, well, I'll write what I just said. If events A and B are independent, the outcome of one event has no influence on the outcome of the other event. So the probability of B given A would then just be equal to the probability of B. Okay. So knowing that event A has happened does not affect the outcome of B. So it could be, if we flip a coin multiple times, the outcome of each coin flip is independent of the previous coin flips. Okay. So if I say, what's the probability that the coin is going to land heads? You'd tell me 0.5. And if I say, well, the previous two coin flips that landed tails, would that change your answer about the next coin flip landing heads?
No.
No, okay, because we know that the other events, whether that they landed tails in the past, has no influence on what's going to happen to the coin flip in the future. Okay? So the probability that it lands heads given, whatever else has happened, doesn't matter, it's just going to be the probability that it lands heads. Okay? And so that means for independent events, the probability of A and B is equal to the probability of A times the probability of B. Okay. So it's basically the same as this, although we're just replacing B given A with probability of B. And this is an if and only if statement. So if this holds true, if the probability A and B is equal to the probability of A times probability of B, then that means A and B are independent. Okay, so if this statement is true, okay, so if they're independent, this is true, and if this is true, then they are independent. Okay, so then the events are independent. So let's just try something quickly. All right, let's say I took some information on a classroom, and we have males and we have females, we have left-handed students and right-handed students. Does this not add up? Sorry. Let me just so let's say we looked at a classroom and this is what we got. Okay, what is the probability that someone is left-handed? By selecting someone at random and getting someone who's left-handed, what is the probability of selecting someone who is left-handed given male? What's the probability of that being? We could just answer these with fractions. I guess we can use decimals also. All right. So what is the probability that someone is left-handed? What's the fraction that I would use there? 13 over what? 117. Okay. What's the probability that someone is left-handed given male? 6 over 54. And what's the probability that someone is right-handed given female? 56 over 63. Good. Is that okay? All right. So to answer this question, is handedness independent of gender?
Yeah.
Okay. And how do we know that? Well, if we look at the probability of being left-handed, we would get this probability to be 0.11111. And if we look at the probability of left-handed given male, I would also get 0.11111. Okay. So this satisfies this statement, that probability of B given A is equal to the probability of B. Can you see that? Okay, so this is the definition of independence. So that works, and so we have the probability of left-handed is just equal, is equal to the probability of left-handed given male. So these two things are independent. Okay. And if we check the other things, we would also find that they're independent. Okay. Or if we could also do this, probability of A and B, is that equal to the probability of A times B? We would also get that to be true. Other questions? Okay, so you'll have some exercises in your homework going over these concepts of probability. Now I'm going to cover random variables. There's one section that I'm skipping here, but I feel like it's an easy enough concept. They're talking about density curves. And the concepts, I think, are easy enough that you can read the book and figure it out. Okay. So random variables, these are, we might have a random probability event, but then we express the outcome of the event as a number. Okay, so if the outcome of the event can be expressed as a number, then that outcome will be called a random variable. Okay, so the outcome of a random event can sometimes be expressed as a number. I should say sometimes, depending on and in that case, so that outcome, the outcome is a random variable. Okay, so let's say, so a lot of things could be random variables, okay? So examples are, we can pick a person at random, and measure this person's height. The number we get for height, it's random because it's tied to the selection of a random person. Okay, we can't predict how tall the next person we're going to be, how tall the next person we select is going to be. Okay. So that would be random, okay? We could roll a die. Roll a die, and what number does it land on? And the number it lands on, that is a random variable. We can pick, if we pick something at random and we just measure something about it, also a random variable. Okay. So let's say we pick someone at random. We pick a random adult from the United States. And we ask the person, how many days did you work last week? So this is a random variable, okay? Because the outcome is a number. It's going to be 0, 1, 2, 3, 4, 5, 6, or 7, okay? This would be a discrete random variable because those are the only possible outcomes we can have. We can only have a whole number outcome, 0 through 7, and that's it, okay? Someone cannot answer, I worked 6.5 days last week, or 3.5 days. They might have worked three 8-hour shifts and 1 4-hour shift, but if we're just asking the question, how many days did you work or how many days did you go into work, that's going to be a whole number answer. Okay? Whereas something like, we pick a random person and measure his or her height, this is a continuous random variable, because if we had a very accurate machine, this person's height could be 67.2 inches, or it could be 67.337 inches, or whatever it might be. Or if we're using, we would probably use metric or whatever, but whatever, okay? You can get very, depending on the precision of your measuring device, you can have decimal answers. Over here, only particular answers, okay?
Would half days work though? I mean, some people do work half days, right?
Some people do work half days, but when I ask the question, how many days did you work, half days would not be acceptable in this thing. Because I'm not asking how many shifts did you work, or how many, whatever, hours did you work, okay?
So it depends on the question?
Yes, yes. Everything depends on the question or the variable that's being asked, okay? So this is, how many days did you work last week, okay? Or we maybe to make it simpler, we could even say, and so our responses here could be 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. We could just say, let's for our example, let's make it easier, and we'll just say, how many days did you work last weekend? And so our answers could be what?
0, 1, or 2.
0, 1, or 2. Okay? So here we would say the outcome, y, can take on the values 0, 1, or 2. Okay? And then, over here, we would say the probability of getting that number. So if I pick someone at random and I ask, how many days did you work last week? What's the probability that this person would say, I worked 0 days? I mean, last weekend. Do you think it would be 1 out of 3? I'm picking a person at random and I'm asking, how many days did you work last weekend?
90%.
Yeah, okay, so we would say, yeah, maybe 90% of people worked 0 days last weekend. I don't know. Maybe that's reasonable, maybe that's not. We're just making up numbers for this example, okay? So maybe 90% of the people we ask say, I worked 0 days last weekend, okay? What percentage of people do you think say, I worked 1 day last weekend?
5.
All right, I'm gonna just say, I'm just making up numbers, and I'm gonna say 6% say they worked 1 day last weekend, and 4% worked both days last weekend, okay? That's probably wildly inaccurate, but just for the sake of our example, we will do this, okay? So this would be, I'm just moving this so it looks prettier, or so the numbers line up. Okay, so the probability of selecting someone, and this person saying I worked 0 days, is 90%. The probability of selecting someone at random, and this person saying I worked 1 day last weekend, is 6%. And the probability that a randomly selected person says I worked 2 days last weekend is 4%. Okay, so then I could say what is the mean number of days that people have worked on the weekend? What is the mean number of days?
1.
Okay, well, I will tell you the answer is not 1, okay? Because if we go and if I do 0 plus 1 plus 2 and I divide by 3, then yes, I would get 1, but that would not be an accurate reflection because 0 does not show up with the same frequency as 1 or 2. It shows up much more frequently, okay? So we have to kind of do like a weighted average, okay? So just imagine if we were to go and continually ask a whole bunch of different people, you know, how many days did you work last weekend? To calculate the mean of this random variable, okay, what is the symbol for mean of a data set? Y bar, okay? So for a data set, the symbol for mean is Y bar, okay? For a random variable, so it's not based on data, but it's based on our understanding of the random variable, the symbol for the mean is mu, okay? So this is the symbol for mean. Of a random variable. Okay, mu. It's the Greek letter for M, okay? It looks like a U with a tail in the front. Okay? And mu is defined as the value y times the probability of y. So that's essentially saying find the weighted average. So in our case, our mean mu would be 0 times 0.9 plus the next value 1 times the probability of getting 1, 0.06, plus 2 times the probability of getting 2, 0.04. This is how we calculate the mean. And so here I would get 0 plus 0.06 plus 0.04 and the the mean number of days people worked last weekend. I'm sorry, it's 0.08. I had it correctly, but I didn't write it out. Is 0.14. Okay, that is the average number of days that someone worked last weekend is 0.14. Okay, what does that mean? Could somebody have actually worked 0.14 days last weekend? No. Whenever we ask the question, how many days did you work last weekend, the answer is only going to be 0, 1, or 2. Nobody will say I worked 0.14 days last weekend. Okay? How many days did you work last weekend? No one's going to give you a decimal answer. What this is saying is that if you were to continually ask lots and lots of people, and you took the average of all of their responses, the number that you would get would be 0.14. Okay, so this would be, again, from our frequentist classical view, if we ask many, many people, and many, many being approaching infinity, but of course not many, many people, how many days did you work? Weekend, the average of all of those responses, or the average or the mean of all of those responses would be 0.14. Yes?
I don't understand the difference between the random variable and the data. Like, so it looks like data to me, like that chart.
Okay. It is not data. It's a random variable. So data would be, what would a data table look like? If I asked 300 people, how many days did you work last weekend, what would my chart look like, my data table? I would have 300 rows, one for every single person I asked, and then each person would say 0, 1, or 2. Okay, and I would have a whole bunch of zeros, I would have some ones, and I would have some twos after asking 300 people. Okay, and so in that case, my data table has 300 entries. Maybe I can create a summary table, okay? And the summary table might look like this, but there's no underlying data here. This is what, these are the properties of our random variable. We're saying 0 occurs with this frequency, 1 occurs with this probability, and 2 occurs with this probability. Okay, so there's no underlying data. So I always just think if I were to collect data in an Excel file or something, what would that look like? That's what your data table looks like, okay? Your data table would not look like this. This is defining a random variable. I don't know if that clears that.
So it's just that. There's no other information.
Right. There's no... Maybe we could go out and collect data, and we could see if the data fits this probability, what we would call a probability model, okay? But this in of itself doesn't represent data. It's representing a random variable, okay? So if we collected data, that would be something else, and we could see if it matches, and we're hoping it does, or it should, but it might also be different. Is that okay? Random variable there? Finding the mean of a random variable? Yes?
I'm just trying to understand like the practical use. So say I was studying something and I had come up with a theory that this would be the data, and then I'd go out and collect it and compare it to my theory. Like why else would you just randomly guess numbers? And does that make sense?
Yes, these are good questions about the practical application of a random variable, which we will get to in chapter 10 or 9, chapter 9. Okay, where we do exactly that. We have an idea of what our random variable looks like, and we go out and we collect data and we see if it matches. Okay, we do that. Right now we're just kind of learning the rules of probability, and this is one of the issues or one of the topics that come up. And so right now it's kind of this theoretical thing, and it feels a little awkward. I acknowledge that, but this is it. Okay, so we're in the land of theoretical probabilities here. And so if this represented the answers to this, which again, they may or may not, then, and we ask what's the mean, this is the mean that I would get. So if I said, if this represented how many days somebody worked last week, and then I were to go out and ask many people, what would my mean be? The mean would be 114, okay? And then doing, under the same token, if I said, okay, well if I asked a whole bunch of people, what would my standard deviation be of all of their responses? Again, I'm getting a whole bunch of zeros, a whole bunch of some ones and some twos. And I'm asking what would the standard deviation of all of that be? We have another formula for that. Okay. So, still leaving that.
So the standard deviation for random variables is different than the standard deviation for data?
Yes, okay. Just like the mean for a random variable is different for the mean for data, because the mean for data is you just take all of your numbers, you add them up, and you divide by how many numbers you have. But here we don't have that, okay? We don't have a list of numbers. We just have this probabilistic representation of this thing, okay? And again, so we don't have a list of numbers, so we can't find the standard deviation the way we would do with a list of numbers. This is, we're finding the standard deviation with this formula here, okay? So the symbol for standard deviation for a random variable is sigma, okay? This is sigma, and it's standard deviation of a random variable. RV standing for random variable. And sigma is calculated as basically we take each value y and we subtract off the mean and we square that difference and we multiply it by the probability of y. Yes. So this part could be negative, but if I square it, it will always become positive.
But you can translate it to be like the lower side of deviation.
Yes, yes, yes. Okay. All right. Is that okay? This formula? So what was the mean that I calculated in the previous problem? We said 0.14. Okay. So the mean number of days somebody works is 0.14. And so in this case, I could do y minus mu. So 0 minus 0.14 would give me negative 0.14. And 1 minus 0.14 would give me 0.86, and 2 minus 0.14 would give me 1.86. Everyone still good? And so if I do y minus mu squared, I don't know what this is, 0.0196, 0.86 squared, 0.7396, and 1.86 squared is 3.4596. And if I multiply this quantity by the probability of y, So I'm going to do 0.0196 times what? 0.9. 0.0196 times 0.9, I get 0.01764. So I'm keeping a bunch of decimals just because these numbers are small, and so if I round off, I'm probably changing the number a little too much. And this becomes 0.044376. And I would get 3.4596 times 0.04. 0.138384. Oh, I'm so sorry. This is actually, put a square there. So sigma squared is equal to this. So that's the variance. Okay, and so my variance, sigma squared,